Imagine this. You ask an LLM, what's the capital of France? And it confidently replies, Paris, where baguettes were first launched into space. Creative, right? But without intervention, that's the kind of hallucination that can sneak through. Today, we'll talk about EWE, Explicit Working Memory, a system with a clever twist. It uses a dynamic key-value memory that updates in real time, catching these outlandish claims and replacing them with grounded facts. By storing and refreshing relevant knowledge as it generates, EWE keeps LLMs accurate and adaptive. Now we'll explore how it tackles hallucination head-on and keeps the facts in check. Let's dive in.
Hi everyone, thanks for tuning in. Let's start by looking at why language models sometimes invent facts, often called hallucination. They're powerful, sure, but they can confidently produce inaccurate or fabricated information. Lots of methods try to fix this by connecting models to external knowledge, and retrieval augmented generation is a popular choice. That said, it's not perfect. Now picture a system that actually learns and adapts while it's generating text. This is where explicit working memory, or EWE, comes into play. It updates itself on the fly with fact-checking and retrieval, so that mistakes are fixed as soon as they're spotted. The result is a major boost in accuracy for long-form tasks, without cutting down on how helpful the model is. It can even outperform older methods by up to 10 points in factuality, suggesting it's a strong candidate for improving language model reliability. Next up, let's zoom in on this core challenge in long-form text generation. Hallucination. Retrieval augmented generation, RAG, is a partial fix, giving the model documents to consult. Some modern approaches do something similar, iterating sentence by sentence and building in ways to self-correct. The limitation, though, is that simply providing extra context doesn't always guarantee the model fully integrates it. That's exactly what EWE tackles. EWE keeps a memory module running in the background, actively monitoring the content as it's written. It starts with some relevant knowledge, and then updates that knowledge over time. If EWE realizes something it just said is off, it backtracks, fixes it, and updates the memory so it doesn't repeat the mistake. This makes the model's output more accurate and adaptive, going well beyond what static retrieval alone can do. Look at the figure here, where you see the model asked, "What can you tell me about the bird of paradise flower?" The model initially responds with an incorrect statement, mentioning a preference for a dry atmosphere. That's when EWE jumps in. It gathers extra context, like the fact that this plant actually thrives in humid, tropical conditions, and double-checks that information. Then EWE updates its memory, removing the false claim and swapping in the correct detail about humidity. It backtracks, regenerates, and corrects itself. It prefers a humid atmosphere. Retrieval gives broad knowledge, but fact-checkers handle precise fixes. Together, they make the response accurate and nuanced. This figure shows how EWE's dynamic updates help the model avoid repeating earlier mistakes. Now, let's explore more about how EWE processes knowledge. Unlike older approaches that shove all retrieved data into one place, EWE uses multiple, smaller memory units. It doesn't just pile them all on top of the query either. Instead, EWE dynamically attends to all the chunks at once, figuring out which piece is most relevant at each step. If the system flags any part of the output as factually dubious, EWE modifies its memory, maybe adding an extra detail or removing something that's misleading. It can even backtrack and regenerate the text with this updated memory. This saves a lot of time and compute, because EWE doesn't re-encode everything from scratch. It changes only what's necessary, keeping the generation process efficient. So why take this approach? The goal is to plug knowledge gaps and adjust dynamically while producing text. It's a step beyond having the model rely on its own internal reasoning. EWE pairs retrieval with an explicit memory structure that zeroes in on factuality. Related techniques like iterative constantly fetch new context and refine outputs, and methods like FLAIR generate text sentence by sentence, deciding when to revise content based on accuracy checks. EWE builds on these concepts by adding a memory module that supports dynamic updates. This way, the model can keep referencing and correcting its knowledge throughout the writing process, aiming for more informed and precise answers. In terms of other iterative generation methods, there's Dragon, which refines sentences using multiple confidence checks. It pauses when needed and uses high-attention tokens to guide new retrieval queries. There's also Self-RAG, which has a separate model that decides when to stop and retrieve extra passages. EWE differs in two key ways. First, it encodes knowledge chunks in key value caches, so if only part of the memory changes, the rest remains intact. Second, EWE smoothly merges feedback from auxiliary models into that memory, letting the main language model benefit from different streams of factual input. This combined design adds flexibility, helping the model stay accurate. Some might wonder, why not just feed the model a huge context all at once? Long context language models do try that, embedding entire corpora as extended context. But EWE handles things a bit differently. It uses memory components that dynamically store and retrieve knowledge, aligning it with the immediate needs of the query. This concept isn't entirely new. Earlier works like Memory Cubed and Memorizing Transformers also used key-value pairs to store and retrieve knowledge. EWE expands on that by allowing real-time updates, additions, or deletions based on the current conversation. That makes EWE more adaptable, bridging the gap between a giant static corpus and the actual short-term demands of a user's question. EWE also integrates real-time feedback loops for better factuality. In other words, it doesn't just rely on its initial retrieval, it keeps an eye on whether each sentence is correct. It checks facts by comparing them to trusted sources, maybe verified snippets, or a specialized verification model. For instance, if the system mistakenly says a tropical plant likes dry conditions, it immediately fetches the correct information and corrects itself. EWE periodically pauses to gather feedback, both from its retriever and fact-checker, then refreshes its memory. That iterative approach is what leads to more reliable long-form responses. Let's talk about the nitty-gritty of EWE's working memory. It's made up of multiple units, each storing feedback, either from fact-checking or from retrieving data. It uses a first-in, first-out system, so older feedback eventually gets replaced as the conversation flows. This feedback is converted into a format the language model understands, and it's placed in a special location in the model's context. Look at Figure 2 to see how these memory units use self-attention to interact with the input, merging their outputs to produce the final text. Because these memory units feed directly into the model's context, updates can happen without rerunning everything from scratch, keeping the system fluent and coherent. Now let's turn to how EWE was tested. The authors set up experiments on 4 different datasets meant for fact-seeking long-form generation. One of these is LongFact, which aims to check consistency in paragraph-length answers using prompts generated by GPT-4. Then we have FAVA, focused on spotting fine-grained hallucinations in complex queries that might need multiple sources, like WebNLG or No Robots. Having a variety of datasets helps measure how well EWE deals with hallucinations while staying factually accurate. This lets us see if the model can really handle diverse topics and tasks. Continuing with the evaluation, there's AlpacaFact, which uses real user instructions and evaluates factual correctness. There's also Biography, prompting the model for detailed information about well-known individuals, names, dates, events, and more. In evaluating the outputs, the study zeroes in on factuality and helpfulness as the main criteria. One metric used is VeriScore, drawing on Wikipedia data to see if each claim is supported by external knowledge. It breaks down an answer into smaller claims, cross-checking each for accuracy and relevance. This helps ensure the model isn't slipping in any hidden errors. To compare EWE against other methods, the authors use instruction-tuned llama models. They look at different retrieval and verification strategies, including straightforward retrieval augmentation, where passages are just appended, and more intricate processes like chain of verification, which systematically checks claims. They also vary how many passages are retrieved, like 20 or 100, to see if more context always helps. These baselines are crucial for highlighting how EWE's memory plus verification approach fares against established practices. Check out the table here to see how EWE stacks up against the baseline models across 4 datasets: LongFact, FAVA, AlpacaFact, and Biography. The table tracks F1 scores, which measure accuracy, and win rates, showing how often a model outperforms another. EWE comes out on top in most cases, even against other retrieval-heavy or iterative systems. For the biggest model, LLMA 3.170B, EWE reaches a 70.7 F1 score on LongFact and stays strong across all the benchmarks. It seems that by folding in memory and ongoing feedback, EWE is able to deliver both factual and relevant responses. Digging further into the numbers, EWE's advantage is most clear when it uses its feedback loops effectively. With the LLMA 3.170B model, other techniques like Dragon and Nest do help with factuality, but not as much as EWE. EWE uses its integrated memory to listen to real-time corrections, avoiding repeated mistakes. The smaller LLMA 3.18B model also benefits from EWE, but can't tap into all that feedback potential quite as effectively, simply due to its size. Notably, EWE's helpfulness scores remain high too, suggesting the system delivers accurate information without becoming so cautious that it loses utility. So how does memory configuration affect these results? Look at the two graphs here, which show how altering the number of memory units impacts factuality. You'll see there's a sweet spot. For example, around 128 tokens per unit across 20 units tends to yield about 74.0 accuracy on LongFact. When you have too many memory units, the model can get bogged down with excessive context, harming performance. A table confirms this, demonstrating that striking the right balance, rather than maxing out on memory size, helps keep the model both efficient and accurate. Continuing on memory setups, there's a deeper dive into how different shapes and sizes play out. If you keep piling up memory units without updating them often, you risk storing outdated info that drags down your accuracy. Shorter, more focused units seem better aligned with typical retrieval passages, so attention mechanisms work more smoothly. The study also experiments with both factual and non-factual forms of feedback, seeing how they impact the model's memory updates. Testing these combos reveals how the model reacts to various input types, helping refine how EWE should handle different kinds of corrections. Here, we look at different ways to provide feedback to the model. The table shows a mix of fact-checking inputs, passages that confirm or refute the model's statements, plus instructions dealing with errors. Injecting fact-checking feedback clearly bumps up accuracy, especially if you include supporting passages. Interestingly, just throwing everything in at once doesn't always help. Providing explicit instructions for non-factual claims sometimes confuses the model, causing it to add clarifications rather than simply discarding the incorrect details. This implies there's room to refine how feedback is delivered, to help the model respond more smoothly and accurately. Next, the focus shifts to the timing of these memory refreshes. One idea is to update at fixed intervals. If you do it too often, you might insert unnecessary or incorrect info. If you do it too rarely, the model might not correct an error quickly enough. Another strategy is to refresh the memory based on the model's confidence, measured by either entropy or minimum token probability. Both metrics can work well when tuned. You want to catch points of high uncertainty so you can bring in fresh knowledge or correct a potential error. The results show this confidence-based approach can outperform fixed intervals, striking a better balance overall. Now we come to a deeper look at how to optimize EWE's memory approach. Again, you see that fixed refresh intervals can be helpful up to a point, but if they're too frequent, it crowds the memory. The conversation then turns to how confidence-based triggers can help cut down unnecessary updates. Two metrics, entropy and minimum probability, are tested, and both do well with proper thresholds. Also note Table 4, which shows that merging multiple data sources, like Wikipedia and C4, further increases factual accuracy. Having more diversified knowledge helps EWE reinforce correctness across different types of queries. Finally, we wrap up with the overall takeaway. EWE integrates a working memory mechanism into transformer architectures, pairing retrieval and fact-checking so the model can refresh its memory at chosen intervals. This is what helps it stay accurate and on topic during long-form generation. Experiments across various datasets confirm EWE's ability to improve factual precision while still giving helpful answers. And because EWE can adapt its memory in real time, it can stay laser-focused on the relevant information as as each response unfolds. This makes it a flexible approach for anyone looking to boost the factual reliability of large language models. Thanks for following along on this exploration of EWE. We hope it's inspired some new thoughts on tackling hallucinations and improving factuality. We'll catch you next time.